Welcome to the deep dive. Today, we're plunging into a really fundamental question swirling around large language models. Is the way most of them are built right now the only path to powerful AI?
It's a great question, yeah. Because, for a long time, the field has really been dominated by what's called autoregressive modeling.
Right, the next token prediction thing.
Exactly. Think of it like building sentences one word or technically one token at a time, always predicting the very next piece. But the research we're diving into today presents a fascinating alternative.
Okay, we've got a stack of sources here, and they're centered around a paper introducing something new, LLada. LLada.
Stands for a large language diffusion model.
Got it. So our mission in this deep dive is to unpack what LLada is, how it radically differs from those standard autoregressive models you just mentioned, and crucially, what its performance and capabilities tell us about maybe the future landscapes of LLMs.
Exactly. We'll get into the core ideas, see how they actually built and trained this thing, and then really look at the experimental results the paper shares.
What kind of results?
Especially on capabilities you really care about, right? Like how well it scales, if it can learn from examples you give it in the prompt.
Context learning, yeah.
Right. Instruction following, too. And tackling this particularly tricky problem they call the reversal curse. Get ready for some pretty surprising facts they seem to have uncovered.
Okay, let's unpack this then.
Okay.
You hear a lot about large language models falling under this big umbrella of generative modeling. At its heart, that just means they're learning the underlying patterns, the structure of data text, in this case. But while most of the big LLMs use that autoregressive formulation, predicting token by token, left to right.
The standard way.
Yeah. LLada takes a completely different approach. It's rooted in something called diffusion models.
That's right. And what's fascinating here is that diffusion models, they first gained massive traction generating images. You've probably seen those AI tools making amazing pictures from text prompts.
Oh, yeah, definitely.
So for text, LLada uses a kind of similar core idea. There is what they call a forward process, where tokens in a sentence are gradually masked out, sort of obscured.
Masked out, like hidden.
Exactly. Imagine starting with a clear sentence and just progressively hiding more and more of the words over time.
Huh. So, okay, instead of predicting the next token in the sequence, LLada learns how to undo that masking, the opposite.
Precisely. It learns a reverse process. The model itself, which they call a mask predictor, is trained to look at one of these partially masked sequences and predict the original, the unmasked tokens.
Okay, but which masked tokens? Just the next one.
No, and this is key. It can predict any masked token, potentially all of them at once in a given step, not just the next one in line.
Yeah.
And this inherently allows it to model dependencies bidirectionally. It can look left and right at the same time, unlike that strict left-to-right flow of the standard autoregressive models.
Right. They can only look backwards.
Exactly. So during generation, LLada iteratively applies this mask prediction. It refines the text sequence step by step, filling in those masked blanks until it arrives at a fully unmasked, coherent output.
So it's like filling in the blanks, but it can fill in blanks anywhere in the sentence, not just tacking things on the end. That feels, fundamentally different.
It really is. And like I said, it predicts potentially all the masked tokens simultaneously at each step during inference, during the generation process.
How is it built then? Is the underlying tech completely alien?
Well, the sources detail that LLada actually uses a standard transformer architecture for this mask predictor.
Oh, okay, so transformers are still involved.
Yes. If you're familiar with how autoregressive LLMs are built, it's structurally similar, but, and this is crucial, it doesn't use the causal mask.
The causal mask.
Right.
That's the bit that forces the model to only look left-right.
Exactly. That's what enforces the autoregressive next token-only prediction. LLada doesn't have that constraint.
And they built this kind of model, like, at a decent size. From scratch.
They did. The paper talks about training two versions, one with 1 billion parameters and a larger one with 8 billion parameters.
8 billion is pretty substantial.
It is. And that LLada 8B model was pre-trained on a huge data set. We're talking 2.3 trillion tokens.
Wow.
And to give you a sense of the scale, the compute cost, that required 0.13 million H800 GPU hours.
H800s. Those are serious chips. That's a lot of compute time.
It's a massive amount of compute. This wasn't just a small academic experiment. They clearly invested heavily to see if this diffusion approach could genuinely scale up, like the autoregressive models have.
Okay, so that's a significant commitment of resources just to prove the concept at scale. Once they had this big base model, how did they get it to actually follow instructions, be a helpful chatbot?
Yeah, good question. That's handled through supervised fine-tuning, or SFT. It's a pretty common technique now.
Okay.
They took the pre-trained LLada 8B and then fine-tuned it on a data set of about 4.5 million instruction response pairs.
So question-answer examples.
Basically, yes. But the interesting part here is how they applied the masking during this SFT stage. They only masked the response tokens, the answer part.
Oh, okay, not the prompt.
Right. They left the user's prompt, the instruction, completely unmasked. So this specifically trained the model to generate the correct answer based on the question or instruction it was given.
Okay, got it. So standard-ish transformer architecture, scaled up, trained on tons of data. But the core engine, the way it generates text, is totally different, this iterative masking and predicting thing.
Exactly. It's a fundamental shift in the generative process itself, not just next word prediction.
Okay, here's where it gets really interesting, I think. The paper backs all this up with experimental results, claiming this diffusion approach can actually achieve the core capabilities we expect from modern LLMs. First up, scalability. Does it scale?
Right. The sources show LLada scales pretty effectively. They measured its performance up to a significant computational budget, something like 10 to the 23 FLOPs.
Yeah, it's a lot of calculation.
It's a measure of the total computational work during training, yeah.
Yeah.
And they compared it against their own versions of autoregressive baselines built with a similar amount of compute.
How did LLada do?
What they found is that LLada is competitive with these AR models. And interestingly, on specific tasks like MMLU,
That's a big general knowledge test.
yeah, massive multitask language understanding. That one, and also GSM-8K, which is a grade school math problem-solving benchmark, LLada actually showed stronger scaling curves on this.
Stronger. Wow. So that kind of pushes back on the idea that only autoregressive models get massively better just by throwing more compute and data at them.
It seems to, yes. It directly challenges that assumption, suggesting diffusion models can also benefit significantly from scale, maybe even more so on certain types of tasks.
Okay, scalability looks promising. What about in-context learning? You know, the ability to learn a new task just from a couple of examples in the prompt itself.
This is actually one of the most impressive findings, I thought. LLA8B, using just its initial pre-training, so no instruction fine-tuning yet.
It's just the base model.
Just the base model, yeah. It was competitive with LAA3-8B, which is a top-tier open autoregressive model of a similar size, and it actually surpassed LAMA27B on nearly all of the 15 standard zero-shot or few-shot learning tasks they tested.
Surpassed LA2. Just from pre-training. That's pretty remarkable for a totally different architecture.
It really is, and the sources, the researchers, they kind of suggest that this ability, this in-context learning, it probably arises from the fundamental generative modeling principles and just the power of scaling these big transformer models up.
Rather than something specific to autoregression itself.
Exactly. It might be a more general property of scaled generative models regardless of how they generate.
Okay, that's fascinating. And what about instruction following after they did the SFT, the supervised fine-tuning?
Yeah, the sources include some examples like transcripts of multi-turn dialogues that demonstrate the SFT step significantly boosts LLada's ability to follow complex instructions and, have a coherent conversation.
Does it feel like talking to, say, ChatGPT or Claude?
Well, they are pretty transparent that LLada hasn't yet gone through the more advanced alignment steps, like reinforcement learning from human feedback, RLHF.
Right, which most of the big chatbots use now.
Exactly. That's standard for models like LMA3 Instruct or GPT-4 to make them safer, more helpful, less likely to go off the rails. So LLada isn't quite at that level of polish yet, but it still shows impressive conversational ability just from that initial SFT step.
Okay, now this reversal curse, you mentioned it earlier, it sounds ominous. What is that exactly?
It is, and it kind of probes how deeply these models really understand the relationships in the data. The sources describe the reversal curse as this known weakness, particularly in the standard left-to-right autoregressive models.
Okay.
Basically, if you train them heavily on a statement like, I don't know, A is B, say Paris is the capital of France,
Got it.
they learn that forward relationship very well. But they often really struggle if you ask the reverse, what country has Paris as its capital? They might not easily make that backward inference, even though it seems obvious to us.
Huh. Because they only learned it in one direction.
That seems to be the issue, yeah. They learn the sequence Paris is capital of France, but not necessarily the underlying reversed relationship.
And LB tackles this differently.
Yes, and the results they show are quite striking. They designed this clever test using a poem completion task with Chinese poems.
Okay, I have that work.
They asked the models to do one of two things. Either generate the next line of a given poem, that's the standard, forward direction, or generate the preceding line, the reversal task.
Oh, okay. Generate the line that came before. That's tricky.
It is tricky, and look at the data they present. State-of-the-art models, even really powerful ones like GPT-4o and a strong Chinese model called Qwen 2.57b Instruct, they perform very well on the forward task, predicting the next line.
As you'd expect.
Right. But their performance drops sharply when they're asked to generate the preceding line. They really struggle with the reversal.
And LA.
LLada 8b Instruct, the fine-tuned version, shows consistent performance across both the forward and the reversal tasks. It does almost as well going backward as it does going forward.
Consistent. Wow.
And here's the kicker. LLada 8b Instruct actually outperforms both GPT-4o and Qwen 2.5 on the reversal task specifically, and not by a little bit, by a considerable margin.
Wow. Okay, that's a really specific, concrete example that drives the point home. It's not just some theoretical difference in how it works. It actually shows up as a strength on a task where others falter.
Exactly.
And the sources suggest this is because LLada doesn't have that built-in left-to-right limitation because of the bidirectional thing.
That's their strong hypothesis, yes. Because LLada works by predicting masked tokens anywhere in the sequence, looking both ways, it naturally handles information flow bidirectionally during its generation. It doesn't have that inherent forward bias, making it seemingly much more robust to these kinds of reversal tasks.
So, okay, let's zoom out. What does this all mean for you, our listener, trying to keep up with this just dizzying pace of AI development? Why is LLada something you should, know about?
Well, I think it fundamentally challenges a core assumption that's really guided LLM development for years now. Kind of felt like autoregression was the golden path, maybe the only path, to get these models to show amazing capabilities like in-context learning or following instructions well or just scaling up effectively.
Right. It seemed like the proven formula.
Exactly. But LLada demonstrates that you can potentially achieve these same powerful abilities through a completely different mechanism, this masked diffusion approach. It suggests that maybe it's the underlying generative modeling principles combined with the sheer power of scaled transformer architectures that are the real drivers here.
Not necessarily the specific step-by-step left-to-right generation process itself.
Precisely. It just blows open a whole new avenue for research and development, looking beyond the current autoregressive standard. Maybe there are other ways, too.
It definitely offers a different perspective and clearly shows potential for perhaps unique strengths like that reversal reasoning capability. But the sources, they aren't saying LLada is, perfect or ready to replace everything tomorrow, are they? They do point out limitations.
Oh, absolutely. And they're very upfront about this being sort of initial large-scale work. One limitation they mention is that their direct head-to-head comparisons with autoregressive models they built themselves were constrained by their compute budget.
So not quite apples to apples at the absolute highest end yet.
Kind of. A full, massive scale comparison is probably still needed to really nail down the scaling differences definitively. They also point out they haven't yet explored specialized architectural tweaks just for diffusion models in language or system-level optimizations like KV caching.
KV caching. That's a big efficiency booster for autoregressive models, right?
It is, yeah. It helps them process long prompts and generate text much faster. LLada doesn't benefit from that particular optimization yet.
And size-wise, it's not yet competing directly with the absolute biggest models out there, like GPT-4 or Gemini.
Not yet, no. LLada at 8 billion parameters, while significant, is still quite a bit smaller than the true frontier models GPT-4, Gemini Ultra, Claude 3 Opus, and so on. The researchers themselves acknowledge that further scaling is definitely needed to see how it really stacks up against those giants.
Okay. And the alignment piece, too.
Right, exactly. As you mentioned, LLada hasn't undergone that extensive reinforcement learning alignment process, the RLHF, or similar techniques. That's become pretty standard for the top chat models to ensure they're safe, helpful, follow instructions reliably, and align better with human preferences. That's still future work for LLada.
So lots of other areas that are common in AR models, like maybe handling images too, multimodal stuff, or advanced prompting techniques, or using them in AI agents. Those are probably unexplored for LLada as well.
That's right. The paper focuses on establishing the core language capabilities. All those other advanced applications and integrations are likely still on the to-do list.
Okay, so really exciting, promising results. It demonstrates a viable, potentially stronger alternative path for building LLMs, but definitely still quite a bit of work ahead to unlock its full potential and see where it truly fits.
Precisely. I think the big takeaway is that LLada successfully establishes diffusion models as a credible, promising alternative to autoregressive models, specifically for language generation. It really challenges the prevailing norm. It shows impressive foundational capability, scalability, and context learning, instruction following, and it hints at unique strengths, like in that reversal reasoning task where the standard models seem to struggle.
It really proves that sometimes, when you hit a wall or see limitations with one approach, looking sideways, maybe even borrowing ideas from a different domain like image generation, can uncover surprising new possibilities.
Indeed. This whole deep dive into LLada really makes you think, doesn't it? I mean, if diffusion models, which started out learning how to reconstruct blurry images, can be adapted so successfully to understand and generate text by learning to essentially fill in the blanks bidirectionally,
Yeah.
what other generative modeling paradigms, maybe ideas we haven't even seriously considered for language yet, perhaps drawn from completely different scientific fields, might hold the key to unlocking future generations of AI? Maybe AIs with strengths and weaknesses that are totally different from the models we use today.
It's a fascinating thought, something to definitely consider as you encounter and interact with all these different language models in your own work and explorations.